everybody. Goedemiddag. My name is Xavier Attendu, and I'm one of the students working under Professor Faber. And he asked me to participate in this class, which I most gladly would like to do. And today I'm going to be talking a little bit about fibers in biomedical optics. Before I start, if you can and if you want, it would be nice if you activated your cameras just so I can have a little bit of eye contact. Of course, if you'd rather not, that's fine too. But if you don't mind, that would be nice for me. Hi. Yeah, just so I'm not talking to a wall for an hour or so. All right, so fibers and biomedical optics. So over the course of the last couple of weeks, you've had a bunch of classes on all different techniques of biomedical imaging. But one of the big parts of biomedical imaging is also endoscopy. So endoscopy in general is going inside the human body in order to see what's going on, as I said, inside, rather than having to cut it open or to have it take a part out and analyze it outside of the body. It helps when you can bring a device inside the human and do your analysis in vivo, so to say. So fiber technology is a huge part of that, especially with all the optical techniques. We're going to be talking a little bit about that. So there we go. So very briefly about me. So I have a background in engineering physics. So I'm not a physicist, I'm an engineer. And I'm currently doing a PhD in collaboration between Polytechnic Montreal in Canada and the Amsterdam, previously AMC, now UMC, under supervision from Professor Faber. So I came to Amsterdam because not surprisingly, but Amsterdam and the Netherlands as a whole is actually a huge player in terms of biomedical imaging. They have some really big names for optical coherence tomography. So Professor Faber, Ton van Leuven, Professor de Boer are all very big names in the OCT community. And there's also other techniques such as a single fiber reflectance spectroscopy, which I'll talk about a little bit, which are actually Dutch inventions. And so I came here to benefit from all that expertise, and also to run away a little bit from Canada because the picture you see right there is a park near my parents' house last week. So we're in May and it's still snowing, it's still cold. So whereas you have nice 20-degree weather here. So that's nice to get away from that. So my personal research is centered around the development of multimodal OCT. So it's always OCT plus something else. And that something else here in the Netherlands is mainly single fiber reflectance spectroscopy. And just as a quick overview, the idea is that with OCT, you can have access to the morphological information. So you've had the classes on OCT, and you know that it's a very powerful technique to assess the different layers of tissue and the structure of those tissue beneath the surface. One thing it doesn't do is it doesn't give you so much molecular information, at least in the standard implementation. And our idea here at the AMC is that we can combine it with other modalities that can give us molecular information. And then you have access to these two complementary sets of information that can maybe help you in diagnosing your pathology. And we're also working on putting all of that into endoscope format using fiber technology in order to do this kind of analysis inside the human body. So very briefly, a little outline. So the class will be subdivided into two big parts, and then at the end we'll talk a little bit about the assignment that's going to be due after this class. So the first part is about fiber technology. So I'll be talking about a little bit about waveguides and the fundamental theory of waveguides and how light is guided through planar waveguides and fibers, and where certain parts of the theory break down, and then you have to revert to other theory. So namely, when geometrical optics stops working and you have to revert to wave theory. And then I'll talk briefly about some essential fiber components and what they do, and give some an overview of different applications in biomedical optics that do require fiber. And a lot of it is going to be techniques that you've seen in previous classes, just with the added fiber components that allow endoscopic imaging. And then finally, I'll talk a little bit about the assignment. So the assignment is going to be an experimental system design. And the idea of that assignment and also of this class is to kind of highlight the duality that there is between science, like real, just fundamental scientific work, and engineering, and how you can't really do one without the other. And in biomedical optics, where our objective is to develop novel technologies that better detect diseases or better diagnose certain conditions, there's always both of these fields are involved. And so the idea is that today I'll talk about the technology of fiber and the science behind that. And then in the assignment, we'll look at some technical challenges that you may have during system design, so that you can kind of get familiar with the kind of issues that you can have. So, the very beginning. So waveguides. The very, very first public demonstration of guiding light through something was done by John Tyndall in the 1870s. And it's an experiment that I think most of you have seen, where you shine a light into a glass, and then if you let somehow a little bit of that light escape, the beam will be bounced around inside the water that's escaping from there through the phenomenon called total internal reflection. By the way, if at any point anybody has any questions, please don't hesitate to stop me. So if there's anything unclear or anything, just jump right in and ask away. Okay, so phenomenon of total internal reflection. So I'm sure that you've all heard about this, probably studied it, but at least heard about it. So total internal reflection is a very, very simple phenomenon that can be explained with Snell's law. So Snell's law is the simple equation that describes how light is refracted when it passes from one index of refraction to another, that you see right here. Can you see my mouse when I'm on screen? Can I get the thumbs up from Cyril? You're the only person I see on camera right now. Do you see my mouse now? Nope. Now? Okay, perfect. So if the index of refraction, so if the initial index of refraction, N1, is greater than N2, there exists an angle for which the light will be totally internally reflected. So basically what happens is when theta 2, when you solve Snell's law, and when theta 2 reaches 90 degrees, light is no longer transferred from the first medium to the second. And you can solve very simply to get this this critical input incidence angle with the equation that's right here. And so as soon as your incidence angle, so the angle between the normal, so the red beam and the normal to the surface, is anything greater than the critical angle, there's no more refraction, light isn't transmitted to the second medium, and it's totally internally reflected. That's kind of the simple explanation. A slightly more accurate description is to say that the momentum of light across the interface must be conserved in the x direction. So then if you look at the momentum and or the speed of the wavefront, that has to be continuous. So if you do the projection of the speed of the wavefront in both media, they have to be equal, which is essentially the same equation as right here, because the wavefront has to be continuous. Ave, everything okay?
Oh,
Yep. Okay, sorry. No, I thought you might have something to add. So yeah, it's a result of the conservation of momentum and the continuity of the wavefront that there is total internal reflection. So that's the geometrical explanation. So what happens when we try to use that phenomenon in order to get light where we want it to go from point A to point B? So if we have a structure that we call a planar waveguide that consists of two materials, Nx in this diagram, or the core index, and Ng, which is the outside index, which we will call the cladding index. And this is a hypothetical structure that's infinite in z and y, and has this structure only in the x-axis. So what happens if we shine a beam of light in the z direction? So depending on the input angle that you send this beam of light, different things can happen. So depending on the angle theta z here, which is the angle relative to the axis of propagation, you'll have either the light will refract at the interface between the core index and the cladding index, and then some of the light will escape while some of the light will be reflected inside. Or if the angle of incidence theta I is greater than the critical angle, then you'll have total internal reflection and no light will escape outside of the structure and it will just bounce inside. Now it's quite easy to show that if that's true for the first interface, it'll also be true for every other bounce after that, right? And that's what happens, that's what we call guiding light, is when you have a structure that keeps the light inside and bounces it along the direction of propagation forever. If we don't account for the losses due to the material, theoretically there will never be any loss due to refraction if total internal reflection occurs. Okay? So the one thing just to notice is that the angle, the critical angle for total internal reflection that's defined by Snell's law uses the angle of incidence. Now the angle of incidence is the angle between the ray and the normal to the surface. In most of the math that I'm presenting here, we're going to be working with theta z, which is the angle of the beam relative to the optical axis, or to the direction of propagation, which is usually the z-axis. Just be aware that then you get this new definition of the critical angle, which is just the cosine instead of the sine, or the inverse cosine instead of the inverse sine. Alrighty. So, like I said, you have two scenarios. One where there is some light that refracts and exits the waveguide, and one when total internal reflection occurs and no light is lost. So the if you've ever done some of the refraction math with Fresnel's equation, you know that the quantity of light that can be refracted can be quite small. So we're maybe talking about 1–2%. But you have to realize that when you're sending light through this waveguide, you're losing 1–2% at every single interface. And so it happens very, very quickly. No matter how small the loss is, it's very quick that they stack up. So we're talking, let's say you have 1% transmitted outside. That means you have 0.99 left. So it's 0.99 times 0.99, and so on and so forth. And so those losses stack up very quickly, and so you eventually end up with no light at all. Which is why we say that there's no guiding. The light isn't guided as soon as you have any losses, whereas here, where theoretically you have none, it is guided. Okay, so to describe rays inside of a waveguide, you can use different approaches. But the main one is to define something called the ray invariant, or the ray path invariant, which is called beta, which is something that never changes along the propagation of the beam. And in the case of a step index waveguide, so a step index, just to be sure, is when you have one index for the core, which is NC, and then one index outside, and there's a sort of step function like this. But when you have a step index planar waveguide, your ray path invariant is simply the cosine of your of the angle. And the cosine of the angle, no matter how many times the ray bounces, the cosine of the angle will always be exactly the same relative to the optical path, the optical axis. And so this this ray invariant is enough to completely characterize the ray that you're looking at. Now, typically then what you do is you express the condition for a ray being guided as a function of this beta bar, which is simply if your angle of incidence is between, so here again, so if your angle theta z is between 0 and the critical angle, then you will have guided rays. And if it isn't, if it's anything larger than the critical angle, then you will have refracted rays and you do not have guiding. And then you can reform this into a different expression that basically says if your beta bar is between the index of refraction of the core and the index of the refraction of the cladding, you will be guided. And if your beta bar is smaller than your the index of refraction of the cladding, you won't be guided. Okay, so beta bar is called the ray path invariant. It can also be called the effective index. Okay, as you can see here in the refracted ray little equation, you're directly comparing beta bar to the index of the cladding and of the core. Okay. So using simple geometry, we can define all sorts of properties of these rays that are bouncing around in this waveguide. One of them is the geometric and the optical path between two reflections. So very simply, if we start from point P to point Q, we can do the trigonometry, and we know that the total path length is the hypotenuse of the triangle right here, which is simply 2 rho, where rho is the radius of this waveguide divided by the angle at which the ray is propagating. And the optical path length is just the geometrical path length multiplied by the index of refraction. Similarly, you can calculate the distance in the z direction from P to Q, which is just given by this equation. So so one thing you have to realize is that if you take two rays that are bouncing around at different angles, the geometric and optical paths aren't going to be the same. So one ray is going to travel a longer distance than the other, and therefore it's going to take longer to get from one end to the other of the waveguide. So the phase velocity along the waveguide, so the projection of the phase velocity along the waveguide, is given by this equation, and that's just how fast the wavefront is propagating in the z direction. And the group velocity is I'm sure you've had explanations of group and phase velocity, but the group velocity is basically it's the projection of the speed of the ray onto the optical axis, and that tells us how fast the optical axis is moving in the z direction. And what you see is that here this speed depends on the angle of the ray. All right, and then the group propagation time is just the distance divided by the speed. So, big point to realize, and it'll be clear why this is important in a few minutes. But different rays traveling through different paths will travel at different effective speeds at different group velocities. Okay. There's other effects as well. So we're not going to spend very much time on this, but basically the index of refraction is a function of the wavelength, as I'm sure you've heard before. And so since the index of refraction is a function of the wavelength and the group velocity is also a function of the index of refraction, it's logical that beams won't propagate through a waveguide at the same speed, depending on their wavelength. Okay? So you've had in your previous classes the theoretical explanation for the index of refraction, which is the Kramers-Kronig relationship. A different way of describing the index of refraction, which is purely empirical. So this is just based on experimental measurements that tons and tons of people have repeated and repeated. You can describe the index of the refraction using the Sellmeier equations. And in optics in general, it's quite useful to have access to good description, and refractiveindex.info is a good place to find the index information for a whole bunch of different glasses and materials. Okay, so taking these very basic concepts, just the first few minutes, there's a first mini assignment just to get you thinking about what's going on inside waveguides that you can see here. Dirk, are you there?